Hi, welcome to our video. This is section 3.6, part 2. I'm going to go through the 3 cases for damped systems in this video. And then the notes that I attach are going to have an example of this. We will also do an example in class together. So this is just really getting to know the 3 different cases. So I'm going to start with case number 1. Seems like a good place to start. And in case number 1, we are going to see a system that is overdamped. Now, this overdamped system occurs when b squared minus 4mk is greater than 0. And just as a reminder, we ended our class on Monday discussing where that discriminant comes from. And that comes from our second order linear my double prime plus by prime plus ky equals 0. So if this is my standard form right there for my second order linear, then I use my characteristic equation with m, b, and k as the coefficients. And then this would be my discriminant greater than 0. So this causes an overdamped system. What does it mean if I have an overdamped system? Well, what would happen in this overdamped is that I would get some oscillation, but it quickly snaps back. And so I would see something where my general solution in this case would be y of t equals c1 e to the r sub 1 t plus c sub 2 e to the r sub 2 t. Again, this should seem familiar. We discussed in class that we would get 2 distinct real roots from this. So my 2 distinct real roots with a general solution that looks like y of t there, this would result in no oscillation. So I said some, but I'll show you in the graph kind of how this happens. It definitely won't be doing any back and forth. And so what's going to happen in my graph here, and you may see something that gets pushed away, either it gets pushed down away from equilibrium or up away from equilibrium. So you may just see a reflection in this graph, but generally this graph is going to go away and then quickly overdamped, come back to equilibrium here. Okay, so this is what the graph of this looks like. So I guess when I think oscillation, I was kind of thinking incorrectly there, but it goes away and then quickly comes back. So oscillation would be if there was any going back and forth. There is no oscillation on this one. In fact, if we were to evaluate the limit as time goes to infinity, we would see that our general solution y of t is equal to 0. So that's my overdamped case. All right. Moving on, we are going to go to case number 2. And case number 2, we are going to see something called critically damped. All right, so a critically damped system occurs when b squared minus 4mk is equal to 0. That will be critically damped. Okay, so for critically damped, there is a light distinction between overdamped and critically damped, okay? But let's just go through really quick. My general solution here will be y of t is equal to C sub 1 e to the RT plus C sub 2 T e to the RT. So this will look familiar because this is the situation where because b squared minus 4mk was equal to 0, we got one repeated root. It is a real root, but it's that repeated root. And so we had the additional factor of t. This one also has no oscillation. So if you think about, it has a real root, it's just one that gets repeated. That causes it to be very similar to our overdamped system that we just saw in the last example here. And so what you might see with something that's critically damped graphically is that, maybe this one bobs away from equilibrium and it comes back, but maybe it comes back a little more slowly. Okay, so overdamped, it pretty much will snap back to equilibrium pretty quickly, whereas critically damped, it may just take a little bit longer. But again, if you were to evaluate the limit here as t goes to infinity, you would see our general solution y of t is equal to 0. All right, so pretty similar, but critically damped versus overdamped is a distinction that we make between those two cases. So let's go to case number 3. These first two don't seem very exciting because there's not any oscillation, but case number 3 will be the exception there. And we kind of lump together where we have underdamped, underdamped, and undamped. So we put these together. Now, we did talk about how our undamped system will look a little bit differently in terms of the standard form, because with an undamped system, you are missing that middle term with the B coefficient. But in both of these cases, what we get is that B squared minus 4mk is less than 0. So these two get put together because our general solution deals with our two complex roots. And so my general solution, y of t, equals c sub 1 e to the alpha t cosine of beta t plus c sub 2 e to the alpha t sine of beta t. Now, again, in our undamped system, that difference would be that alpha is equal to 0. And, and we would just deal with beta in those cases. So we kind of looked at that example today in the notes. And it's the same idea, just looks a little different in practice. So one thing that we could do with this is we could factor out our common factor of e to the alpha t. And in fact, you will see in the book that they use this where we factor out our common factor here. And that leaves us with c sub 1 cosine of beta t plus c sub 2 sine of beta t. And then the reason why they do this is they use a little bit of a trig rule here and rewrite, so that way we could say another way to do this is y equals a e to the alpha t sine of beta t plus phi. So it's just a sine graph with a shift. So you'll see this in the book. It'll kind of define how you get phi in there. We won't use it a whole lot in this class, but I did want to point out that this is a form that could be used and point it out specifically because your book does. So the one thing that does make this a little nicer here is this e to the alpha t is called the damping factor. And again, this will come up when you do have alpha. So in the undamped system, we wouldn't have a damping factor, okay? An easy way to find this is alpha is equal to negative b divided by 2 times m. So we could use that to find alpha here and get our damping factor. Again, we'll look at kind of the two scenarios we get here. If alpha is equal to 0, that is undamped. That's the scenario that we worked with today. So in this case, e to the alpha t, because alpha is equal to 0, would be equal to 1. If you plug in that whole factor right there of just 1, then you would just get this sine graph that gets shifted with that phi term in there. Or if you went all the way back to our standard form up there, what you would see, and I guess this depends on where we start away from equilibrium, but you would see just perfect little sine or even cosine if you start at the maximum there. So the key here is that we get oscillation with an unchanged amplitude. So hopefully I did that graph some justice, because the amplitude should be consistent and unchanged. And that's because it's undamped, right? So there is no damping factor causing it to go back to an equilibrium. Undamped just means it oscillates freely. Now, the other scenario here is that we do in fact have some alpha value that's not equal to 0, and that would be what our underdamped system would look like. So there is some damping, but it doesn't snap directly back to equilibrium. It oscillates for a bit, but with decreasing amplitude. So what we would see for this is it would start the furthest away, and then slowly amplitude would decrease as it works its way back to equilibrium. And it may oscillate more than I have right there, okay? But that's really the key. Oscillation with decreasing amplitude. Okay? And that's really the key there. Really, I would say what we focus on the most. We do see critically damped, okay, that is fair. But I would say more often we see an overdamped system with two distinct real roots, or we're distinguishing between an undamped and an underdamped system with these, okay? And that's really, I mean, you do have to know all of them, but the nice part, it ties right back in with our system of second order differential equations. And so it goes along with the whole idea of having a quadratic. If you have any questions, let me know. You will notice the notes that I post today, they did not save. And so I will post some notes here that are from a previous year. It's all the same ideas. So again, just let me know if you need anything.